Today, I'll be discussing how space ground networks, specifically at the remote terminals, can now harness the wave of innovation that's happening at the space layer. A little backdrop for today's discussion is that we are living in an unprecedented time of innovation in space. With software-defined satellites, massive increases in bandwidth, with the deployment of thousands of spacecraft in many constellations, GEO, MEO, and LEO orbits. Not only can payloads be reconfigured on the fly, but we are also seeing an emergence of inter-satellite links that enable satellites to communicate within constellations and beyond, bringing drastically improved performance and latency. This incredibly dynamic space layer is the answer to the ever-growing demand for internet connectivity to any device, anywhere, at a moment's notice. In the past, space didn't have the capability to reconfigure capacity and coverage on the fly, but rather looked more like a stovepiped connection, purpose-built for one use case, with the satellite acting like a relay. With this new dynamic transformation in space, there's an exciting opportunity to address this need for more flexibility at the space layer, which also requires ground systems to be dynamic, in concert to adapt as business cases evolve and networks scale to meet demand. Kratos is leading the charge with OpenSpace, the first and only software-defined platform for satellite ground systems. But what about the remote terminal? In today's session, I will cover what terminals currently look like in the market, and how Kratos is transforming that model through our innovation with our OpenEdge product line. So with that background, let's jump in. First things first, what is a satellite terminal? A terminal is a communication system that provides connectivity to a remote user via satellite at the far edge of the network. In satellite networks, we typically have a gateway, which is connected to the internet backbone. This provides connectivity to the remote site, which traditionally doesn't have terrestrial connectivity options. For example, trains, maritime vessels, and planes. These terminals look very different depending on the use case, whether fixed or on the move, low data rate IoT, to high-speed trunking, and many other options like satellite frequency bands and waveforms. So let's take a look at what makes up today's terminals first, and then we'll take a look at how OpenEdge transforms the traditional terminal and far-edge deployments to be dynamic nodes in the network. In a traditional terminal, we start with a SATCOM antenna, which can accommodate fixed, comms on the pause, and comms on the move use cases. These antennas take the satellite operating frequency, Ka or Ku band, for instance, and step up and step down to an intermediate frequency known as L-band. This uplink and downlink analog connection to the antenna is then connected to a hardware modem. This takes care of the demodulation and modulation of the signal, as well as encapsulation, ultimately providing user IP traffic on a local area network. These modems and their waveforms are proprietary and purpose-built by each vendor. Additional network functions are traditionally needed at each edge, such as routers and SD-WAN, firewalls, and accelerators, which result in more hardware appliances being stacked at the site with the modem. This adds operational complexity and the need for more specialized installers at each terminal. Today, adapting to network conditions, adding new business cases, and scaling sites require site visits to provision those new changes in an efficient manner. This model uses purpose-built hardware, along with proprietary modems leading to vendor lock-in, and are typically fixed for specific use cases. So terminals today are not flexible enough to adapt as the space layer dynamically changes. With the demand for non-terrestrial networks to seamlessly converge with today's telco networks, this terminal model must evolve. OpenSpace addresses this with a software-defined platform at the core, and OpenEdge addresses these needs for flexibility and power at the far edge of the network with a software-defined terminal. So let's talk about the OpenEdge terminal model. So we start with any terminal antenna based on the use case. Then the first step to making a software-defined terminal is to take the L-band from the antenna and digitize into a standard Diffie packet that can be sent over any local area network or wide area network and is not bound by the typical distance limitations seen in coax or fiber. This digitization step then enables the modem to be virtualized and run in software on general purpose compute. So now let's take a closer look at general purpose compute which serves as the foundation of a cloud-native edge stack. This is known more generally in the telco world as UCPE, Universal Customer Premise Equipment, which is a general-purpose white box platform that integrates compute, storage, and networking on a COTS server that can host multiple CNFs and is located at the customer edge. This includes CPU, RAM, storage, and networking. Next, we have an OS layer, which is our operating system. And on top of the operating system, we have our container orchestration system, known as Kubernetes. In this case, we use K3S for shorthand to represent that it's lightweight Kubernetes. We then can host a pod in the Kubernetes for our virtual modem or multiple virtual modems that can be spun up or spun down on demand. A pod is a group of one or more containers with shared storage, network resources, and a specific way for how to run the containers. This vModem pod is composed of 3 CNFs. CNF stands for Cloud Native Network Function. A CNF is a network function designed and implemented to run inside a container. These 3 CNFs are the modulator, demodulator, and traffic adapter. and make up the V modem, which ultimately provides the means for internet connectivity to the edge of the terminal location. Now that we have a cloud-native stack, we can also onboard third-party applications in addition to virtualized network functions. So the router that was previously hardware can now be virtualized and run in the same environment as a vRouter. Other examples might be software-defined wide area network, SD-WAN, or SASE network functions being virtualized. This network function virtualization provides the following benefits. Lower size, weight, and power at the network edge. Simplified operations at the edge. Accelerated time to revenue. And zero-touch provisioning, which ultimately leads to the operator not needing to send an installer to the end site. Ultimately, all of these benefits equate to lower CapEx, lower OpEx, and an enhanced user experience that allow the operator to meet demand and achieve business goals. This new OpenEdge terminal model, through virtualizing network functions, allows us to use software to replace traditional hardware. Leverage open standards, preventing vendor lock, and transformed what was a fixed terminal into a flexible terminal. This flexible terminal is now a part of a fully software-defined end-to-end space ground segment. To learn more about the OpenSpace Platform and OpenEdge, go to kratosdefense.com/OpenEdge.